Okay, so this is the homework talk video uh, on the first homework for Module 6, acid-base reactions. This booklet is about properties of acids and bases. Okay, let's dig in. So for the multiple choice, question 1, which of the following is Arrhenius base? Okay, Arrhenius states that bases are substances that will dissolve in water and produce hydroxide ions. Okay, and the base itself must contain hydroxide ion. So the only choice here will be B. Okay, so calcium hydroxide is an ionic compound made of hydroxide ions. Question 2, which of the following acids would not have been considered as a acid by Lavoisier? So Lavoisier thinks that acids are those substances that contains oxygen. Okay, so hydrochloric acid, which is HCl, right, does not have oxygen, but it's clearly an acid. So yeah, the choice will be A. In terms of question 3, a bronzite laureate acid is by definition, right, a proton donor. Okay, so just pretty much the definition. Question 4, which of the following species can only be considered as a bronzite laureate base, but not an Arrhenius base? Okay, so Arrhenius says that base must dissolve to produce hydroxide ion. Bronzite laureate says that base accepts a proton. Okay, so this will be a base considered as both Arrhenius and bronzite laureate. This is not a base considered as for bronzite laureate and Arrhenius. This is only a base for bronzite laureate definition, and that's a base for bronzite laureate definition. Okay. So yeah, this one would only be a bronzite laureate base. Okay, what is considered as neutral in this scenario? Okay. Right, and question 5 and 6 utilizes the hydrofluoric acid association, right? So it's a weak acid. So in this reaction above, water in this reaction, right, accepted a proton from HF. Therefore, it must be a base, right? Because it has accepted a proton to become hydronium. So it's a proton acceptor. 6, which of the following is correct? Okay, so A says that water acts as an acid. Its conjugate base is hydronium ion. Actually, here water acts as a base, so that's wrong, and so does B is wrong. C says that hydrofluoric acid acts as an acid, but its conjugate base is hydronium ion. Okay, its conjugate, the conjugate base for hydrofluoric acid is what's left after hydrofluoric acid donates a proton. Okay, so it should be fluoride ion. Okay, this is what's left after HF donated a proton. So the answer for this question would be D. Moving onwards, we have question 7. The following equation represents a chemical system in equilibrium. Okay, nice equilibrium. Which of the following is an acid-base conjugate pair? Okay, so in this reaction, so if we look at A says that so water here is actually an acid here because it donates a proton, right? That means its conjugate base must be hydroxide, which does not satisfy the choice A here. Choice B is very similar, like they are not conjugates of each other. So that's D, okay? Remember that conjugates must be only differed by one proton, okay? So conjugates are only differed. So a quicker way to sort of do this is to look at the two things, whether they are differed by one proton only. Yeah, so C satisfies that relationship. One proton. Give me a sec. Uh, okay. Right, let's continue. Question 8. A piece of aluminum foil is added to a test tube containing diluted hydrochloric acid. what product can be formed. So aluminum reacts with hydrochloric acid, is metal react with a strong acid. All right, so the product would be a salt and also a gas. The gas will be hydrogen gas. Okay, so the reaction goes as aluminum Al, right, solid, plus 3 HCl. Okay, I guess we're gonna somehow balance the equation, and then we get H2 plus Al Cl3, okay, AQ. We're gonna need to multiply this by that. Okay, yeah, and that's it. So yeah, you're gonna produce hydrogen gas and a salt, aluminum chloride. Question 9. According to Arrhenius theory of acid and base, an acid is a substance that, okay, increase the concentration of hydrogen ion. So yeah, that's what he said. He said any acid in aqueous condition is dissolvable, soluble in terms of producing H plus and then A minus. Okay, so it increases the concentration of H plus. Okay, A is just like a generic property, so it's not what we're choosing. B says a capable of donating a hydrogen ion. This will be Bronsted-Lowry definition. C says that it can accept a pair of electrons. This is technically Lewis definition, so it's out of the syllabus. Question 10. It's a calculation question. So a solution of hydrochloric acid is added to sodium carbonate. So I'll just quickly write the chemical reaction. So HCl AQ plus sodium carbonate. All right, so 2 of that will produce H2O plus carbon dioxide. Yeah, this decomposed from the carbonic acid produced, plus a salt, which is NaCl with a 2 in front. Okay, so this reaction produces a gas. Right, and then the question tells you the volume of the gas. Right, it tells you it's at. If you recall, this was RTP, right? In RTP condition, 1 mole of ideal gas corresponds to 24.79 liter of like not gas, right? So you could use this relationship, work out how much mole of carbonate is formed, and hence work backwards to figure out what is my mass of the sodium that's been produced. Okay. All right. Extend the response. Question 11. The students added 4.52 grams of solid magnesium hydroxide into 250 mils of 0.4 moles per liter solution of hydrochloric acid. So the balanced chemical equation goes as such. Okay, so how many moles of water will be produced? So in this question, work out your limiting reagent. Okay, right. If you studied with me in year 11, you should know that like a better formatting, like a formatted way to write out or to determine those limiting reagent questions. Okay, so what I do is I'm assuming that if both like substances in a reactant reacted completely, so there's nothing left, everything just reacts. If you assume that's true, and then the smaller ratio is satisfied, right, and then we're gonna have this relationship being satisfied. Okay, which if you substitute stuff that we know the mass of the first reagent. Actually, we want to find, we know the mass of the reagent, and then we want to find the concentrate or the moles of the water being produced. Right, so we can just plug in stuff that we know. Okay, so we can calculate N1 using M1 and MM1. We can calculate N2 using concentration times volume. Okay, so now you get this equation if everything reacts fully. Okay, but then you want to verify if that's the case, right? So you want to plug in left-hand side of this equation, find out this is 0.0775 mole, and then you plug in the right-hand side of the equation. In this case, you would also consider the molar ratio is half here, give you 0.05, and then you compare these two numbers, right? Which you see how the left-hand side is larger than the right-hand side. So this equation is not really satisfied. We have a limiting reagent here, and then whichever side is less corresponding to the limiting reagent. Okay, in this case, HCl is limiting. So you would use that to calculate, right, the number of moles of water. Okay. Yeah, so doing it this way is like it's more rigorous and it's more sort of robust. Okay, you're not gonna make mistake in terms of molar ratio and then thinking about stuff. Okay, it's very robust. So make sure if you don't know how to do this, make sure you know how to do this method. Okay. Right, and then compare the answer. Answer is should be 0.1 moles times the 3 sig figs. Continue. So an explanation question. This one says that the students then react hydrochloric acid with sodium carbonate. The student noticed that vigorous bubbling. Okay, so bubbling occurred in the solution. Based on the observation, the student made the following conclusion. So the student says that since the reaction between an acid and base produces a solid water, the formation of the gas from between hydrochloric acid and sodium carbonate does not make sense. It does not suggest that sodium carbonate is a base. So he's rejecting that this reaction being neutralization. Okay. Obviously, this is wrong. Okay. So this statement is only valid considering Arrhenius definition, right? So where base ionized in water to produce hydroxide, while acid ionized to produce hydrogen ion. So for the Arrhenius definition, acid-base neutralization must produce salt and water. Like remember that in class we wrote like the net ionic equation, right? It's always H plus plus or H minus. But considering the newer definition, which is the Brownstein-Lowry definition, right, which broadening the definition for base in terms of it, as long as it can accept a proton, does not need to produce hydroxide ion. Okay, well in that case, right, this reaction is HCl donating a proton to your sodium carbonate. So in that case, sodium carbonate in this case is actually considered as a base, and then together they are neutralization reaction. Okay. So yeah, this reaction is considered as a neutralization, and then sodium carbonate is considered as a base. So the student statement based on we produce the gas, that's kind of inaccurate. Okay. So yeah, this is this question. The key here is to sort of compare Arrhenius definition and the new one, the Brownstein-Lowry definition. Okay. Right, and question 12. Describe Arrhenius model of acid and base. Okay, it's pretty much definition. So Arrhenius define acid as like a salt which dissolve into two ions, right? And only works in aqueous condition because of that. And so does the base, right? Produce hydroxide ion. And also define neutralization, right? Because of this definition, we always produce a salt and water. There's two limitations, right? The first limitation, as we go through in class, it only is only applicable in aqueous condition, meaning that the acid-base reaction does not even exist beyond water solution, right? So that's very limited. In fact, it actually does exist. So I give an example where HCl as a gas, yeah, it does like act as an acid, okay? Right, and it's also limited in a sense that many base does not have hydroxide as its ionic component, still act as a base, as in it can accept a proton, such as sodium carbonate, ammonia, right, and all that. Question 13. So write a balanced chemical equation, right? So right, this is pretty straightforward. It should be year 11, and just quickly check your answer. And if you don't know if you're struggling doing this, right, definitely let me know in class and we'll figure something out. But you shouldn't be struggling with this. This is like the basic stuff for chemistry in year 12. Okay, writing chemical reactions and all that balancing, okay, states. Okay, if yeah, I'll zoom out a little bit. So check your answer. If everything is correct, right, you can pause the video. If everything is correct, then we can move on. I'm gonna move on. Question 14 is a graphing question. Okay, the question already has like the data points plotted. So manually, I plotted the white sort of line of best fit. Okay, right. The graph can be split into two components. One is like the linear increase. The other one is like the plateau. Okay. So explain the trend of this graph. In your answer, include a balanced chemical equation and calculation for the mass of the copper and concentration of sulfuric acid. So if you read the question, you should know that the reaction is copper solid, right, plus your sulfuric acid to produce copper sulfate and hydrogen gas. So that gas produced, right, this volume of gas produced corresponding to the volume of hydrogen gas. Okay, so this is a it's a neutralization reaction, and it proceeds to it's not really a neutralization reaction, I guess. I guess you still can, but like copper here is active as a base and accepts a proton, but and all that. Okay. So it goes to completion. So the molar ratio between that and that is 1:1. Yeah. Yeah. So you proceed to consider. So the idea here is, for this question, the best way to answer this, you want us to explain the trend. So, explain why it's linearly increasing. Maybe derive like an equation that tells you this variable is proportional to this variable. Okay, that's what I'm about to do. So molar ratio is 1:1. So the number of moles of hydrogen gas produced is equal to number of moles of sulfuric acid consumed. Number of moles of hydrogen gas can be sort of related to the volume of hydrogen gas, which is y-axis here, using this ideal gas law. And then concentration times volume of the sulfuric acid relates to the volume of the acid added. Then you can just rearrange, right? Rearrange to get your vertical axis, which is the volume of hydrogen gas, and then your horizontal axis, right? You can see how it's a linear relationship with the gradient of bunch of constants, right? So yeah, indeed, we have a linear relationship. This is why we have this linear increase, right? This is the best way to explain. Well, you could also say something like, "Oh, adding more acid produces more of the gas, as like you increase the yield or something." That's not like the best way. The best way for me is to derive this mathematical relationship. Okay. Right, and then you also want to explain say how this is consistent with the graph, right, related to the stimulus, right, interact with it, as that is proportional to that, and then sort of say that up to the volume when the sulfuric acid is added equals to 60 mol, which is here, we have reaction being completed. Okay. After that, no more hydrogen is produced, so we have a plateau, right? And then you could use this value to calculate the mass of the copper and concentration of the sulfuric acid in the solution. Okay, so at that point, you know the number of moles for copper is equal to the mass of the copper divided by molar mass of the copper. That's equals to the number of hydrogen gas produced at that point, which you can use the volume here, right, to work it out using ideal gas law. So it will be 130. Yeah, it should be 130. So did I make a mistake here? This should be 130. So if I use my calculator again, I don't think I made a mistake, but I'll just calculate again just to be sure. 0.13 divided by 24.79 times by 63.55. Yeah. I used 0.13 in my calculator. I wrote 0.12 for some reason. Okay, so that gives you the mass of the copper, all right? Yeah, and then from here to here, I use the RTP condition, right? So I don't have to actually substitute values for P, for T, and for R, right? And then for the concentration for sulfuric acid, right, you can just like using the definition that moles equals to concentration times volume and rearrange it, okay? Right, so this should be your answer. And this should be your answer for the mass of the copper, right? I'll zoom out, and then you can take a screenshot, and then if you're not happy with the original answer, you can copy this down. Okay. Yeah, like this is my way to do this, right? If you have a better way, you can let me know. Okay. Right. Otherwise, I'm gonna move on to question 15, which describes one example of neutralization reaction in medicine and one example in a common household appliances. Include at least two equations in your answer. So neutralization, like for questions like more than 4 marks, I give like a brief introduction, right? This is an example. Neutralization reaction are reactions between acids and bases that goes to completion, right? It has many ways of applications, okay, such as, right, we have the medical use and you split into dot points, right? The question is specifically asked for two applications, so two dot points correspondingly. Okay, so first one is medical use. We have the antacid tablets, okay, which contains base, right? Typically magnesium hydroxide or calcium hydroxide or calcium carbonate. Okay, and then we have a disease where like people have stomach acid disorder, so they just produce a lot of stomach acid and causes ulcer and stuff. This is called the medical term. I actually googled it. It's called hyperchlorohydria. Okay, I can't read this. Okay, hyperchlorohydria. Okay, so it's like a lot of chloride, a lot of hydrogen chloride in the stomach. Okay, so the neutralization will actually took place, right, to produce to reduce the concentration of HCl by neutralization, right? So that's the reaction right here. Reaction going forward, and this is a complete reaction because of neutralization, right? So HCl will actually decrease. Another application is the household appliance, right? So we could use baking powder, which contains this one, soda, and sodium bicarbonate ion. And a weak acid, right? When it's added to water, the weak acid are able to collide, right? Collision theory, collide with our base and produce a neutralization reaction. And that neutralization reaction produces a lot of carbon dioxide gas, okay? And then if you heat it up, those carbon dioxide actually expands, right, inside of your pastry, and then that actually makes the pastry very soft. This is why bread and then all those like pastry stuff, they become tougher, they become very soft, is because the carbon dioxide produced from the neutralization reaction, right? So it's very important in the food industry, okay? Right, so, pause the video, have a read, okay? Otherwise, I'm gonna move on to question 16. Calcium hydroxide is a sparingly soluble ionic compound in water. That's the reaction, okay, in a saturated solution, okay? We know this from from module 5, a saturated solution means maximum solubility, so it reaches this equilibrium state. And then we move on to question B. Students added 3 droplets of concentrated hydrochloric acid to the solution to a saturated solution of calcium hydroxide. Explain the change, right? So immediately after adding a strong acid, the strong acid dissociates into hydronium ion. And the hydronium ion pairs up with the hydroxide ion in the saturated solution, which decreases the concentration of it. And by the Shallish principle, the system will shift forward. Okay, so what you're going to say is because of the addition of the acid, the solubility of calcium hydroxide increases. Okay, by the way, you need to mention LCP here. Okay, so make sure you define it and write equations and all that. Okay, so what I said is that as soon as the sulfuric acid is introduced, this is a strong acid, so it would dissociate into hydronium ion, which neutralizes with hydroxide ion. And then that's the neutralization reaction, hence lowering the concentration of hydroxide ion. By the Chatelier's principle definition, right? Equilibrium shifts to counteract initial change. In this case, okay, relating back to the questions, the calcium hydroxide equilibrium actually shifts towards to minimize the change. That's a fact. Will increase the calcium concentration, or you could add that this increases the molar solubility, increases solubility as well. Okay, right. And then for question 17, assess the usefulness of Brown-Cellari model in classifying acid and bases. Support your answer with these 2 chemical equations. Okay, this question could be very hard. Okay, so like I said, give a definition, right? Just define what Brown-Cellari said. Okay, and then want to assess the usefulness. Okay, so you really want to mention like the good things about it, and right, and then make a judgment. Why is it good? Why do you think it's good? Okay. If you know bad things about it, you could also mention it, right? But you have to make a judgment, right? And then, okay, Brown-Cellari has limitations, but it's not in the syllabus, so I'm not going to include that in our answer. Okay, so I'm only going to be talking about the benefits of it, and I'm going to make a judgment that Brown-Cellari is like perfect. Okay. Also, you need to sort of in order to sort of strengthen your point that it's useful, you need to make comparison with previous model. If you can do that, like make links with Arrhenius model, for example, and what problems of Arrhenius model that end up to be solved by Brown-Cellari model. If you can make those links, you can get very, very high chance that you will get 4 marks for this question. Okay, it's about how deep that you can like engage with the syllabus content. It is not about just writing down definition and stack a bunch of equations together. Those will give you some basic marks, right? Which the marks that you don't want to lose, but they won't give you the full marks for the harder questions like this. Especially we will get to like 8 markers question, 9 marker question. Those questions really like require some of the intrinsic details into the knowledge. Okay, so give the definition first. The Brown-Cellari states it's very successful. Right? That's my the judgment, right? So Brown-Cellari acids says that acids are proton donor, bases are proton acceptors. all that very easy. So say that substances that do not contain hydroxide are considered as a base, right? So Bronsted-Lowry covers more, right? This is an example of Arrhenius limitation, although I didn't really specify that, but it is, right? So Bronsted-Lowry was able to demonstrate this, right? So ammonia as an aqueous condition reacts with water and act as a base in this case. Okay. So the model also explains how acid and base reaction in a non-aqueous state, okay, that so this one I mentioned Arrhenius model. You don't have to do that, but like sort of saying it out is pretty good. Okay, so it was not accounted, but Bronsted-Lowry is very useful, so it counts this, right, by giving the proper definition of acid and base, by giving it its proton donor or acceptor. Okay, and it's exactly what's happening in this case. Okay, this strengthens the point that Bronsted-Lowry model is very useful because its definition is very precise. It covers more yield, covers more field of like acid and base reactions. And then you could also say that in contrast to old model, the Bronsted-Lowry also explains like the role of like chemical substance such as water, like what does water plays a role when an acid is dissolved in aqueous condition, whereas Arrhenius model didn't really have that. It was just like ionization, or it was just like acid ionizes into two ionic components. Water is does not have anything to do with water. But Bronsted-Lowry says that water is like a container that it contains, like it takes the hydrogen ion, or like it produces the hydrogen ion to a base or something. Yeah. All right. So it explains the role of water in aqueous condition. So it gives more definition. And then furthermore, right, if you are very keen, usually if you write the 2 dot points above there, it's probably fine. But I wrote 2 extra just to like reinforce our idea. So another one is like this last dot point. You could say that the Bronsted-Lowry goes into more like theoretical detail, as in it gives us more useful tool, which is the conjugate definition, right? It will be very handy when we get to buffer and later on in the acid-base theory. So it defines more sort of a theoretical framework, right? That makes it very robust and it makes it very applicable in many situations. That's going beyond the theory of acid base. Okay. Right. So the definition of conjugates, right? That makes Bronsted-Lowry very useful. Okay. As we will see, we haven't seen this yet. Yeah, but like we'll see in the future. Conjugates are very important in terms of analyzing acid-base reactions. Okay, so that makes it useful as well. Okay, so we could also talk about limitations. Sorry, right. Do you wanna?
Sorry about that.
Yeah, it's all right. I have to have a meeting in a second. Sorry about it. Okay, so let's continue. So despite from that, you can also talk about limitations, if you know any. Yeah, but like that's outside of the syllabus, so we don't need to talk about limitations. The question doesn't ask it. Okay. And then we have question 18. So question 18 says we need to distinguish between strong and weak acids. And your answer highlights their differences. Okay. And write equations for strong acid, okay, and a weak acid. Oh, actually, I didn't read the question. So the question says, other than hydrochloric acid, and I actually used hydrochloric acid. Okay. Right. So let's just change this hydrochloric acid to something like hydrobromic acid, okay, which is same thing. Okay. Yeah, sorry about that. Okay. So strong acid are defined as like ionized completely in water. Okay, and then definitely use a straight arrow right here, and do not use reversible arrow. That would be very, very wrong. Okay, so as the reaction goes to completion, okay, strong acid dissociation are always irreversible. Okay, establishing static equilibrium. Okay, just mentioning that. And then another point goes to our weak acids. All right, weak acids, on the other hand, only ionize partially. Okay, so you want to use a reversible sign for them, right? I choose acetic acid as our example. You could choose anything else. Carbonic acid, for example, right? They are weak acids. Hydrofluoric acid. Okay, and yeah, just those 2 dot points, right, really makes answering this question easy because it's just the definition and then an equation and then talking about some properties of it, like being irreversible and being like static equilibrium, or being reversible and being dynamic equilibrium. See how the structures are very similar, right? So they follow very similar structures. Okay, that means if I can split this question, any other question in like dot points, I can just use the same structure for the dot points. That makes answering this question very much easier. Okay, so try not to write like a big paragraph, right? Stick with multiple dot points. Sometimes really helps. Okay, right. So it's pretty easy. The question is like you need to answer a lot, but not hard. Question 19. Question 19 says the propanoic acid, okay, is this organic acid thing right here, and then this H here attached to this oxygen is the acidic hydrogen. Although you probably don't understand this, like what does this sort of drawing mean? Yeah, we'll get to this in module 7, but like it's pretty like standard, right? It's like this one will be something like carbon, right? Like any corner represents like a carbon, right? So carbon double bonded to an oxygen, and then also single bonded to an oxygen, and this oxygen is single bonded to a hydrogen, right? That's what it means. So it tells you it's a weak acid, right? So weak acid dissociate like that, reversible error, okay? Given that's 0.1 mole of fat initially, okay? So K is this. The question wants us to calculate the concentration of hydronium ion, okay? Immediately you should look for ICE table, right? You should be realizing this is module 5, okay? Equilibrium right here, start with 0.1, or assume that we're gonna have X moles per liter dissociated, okay? Consider that the Ka is very small, so 0.1 minus X is approximately just 0.1, okay? So for simplicity, we can just ignore that, okay? And then hydronium ion assume is to be 0, not to be 0 and plus X, and then therefore you can say equilibrium constant is equal to X, this times that, X squared, divided by 0.1, okay? All module 5 stuff, rearrange for X, which is concentration of hydronium ion at equilibrium, right? Rearrange it. So 0.1 times Ka square root, right? Substitute numbers, you get this, right? So that's the answer, okay? Should be quite straightforward, right? Some people probably don't realize that we need to use ICE table for this and get confused. But yeah, that's fine. You should be able to realize like this question is not that hard from looking at the answer, okay? If you have questions, you let me know. I'll just explain it, okay? Right, that's it. That's it for this week. It is relatively shorter than physics, okay? All right, so, right. I'll see you next week and then enjoy physics. Enjoy chemistry, okay? And physics, if you're doing both. Right.